Okay, so this is part two of our Frobenius method example. So from part one, where we left off, was we found that r was 0, a0 was 1, a1 was 0, and for k greater than 0, we had this recursive relation here. So we're going to consider two cases here. So the case when k is even and the case when k is odd. So let me write the cases here. So let's say case one is when k is an odd number. So an odd number is basically an even number plus 1. Even numbers are like 2, 4, 6, 8, multiples of 2. So an odd number can be written as 2 times m plus 1. That's how you can write an odd number. And case 2 is when k is even. So an even number is just 2 times m. That would be an even number. So let's consider these two cases. Let's first consider case 1. So under case 1, our k is going to be an odd number, so it's going to be 2m plus 1. So in place of k up here, I'm going to write 2m plus 1 in all these places of k. So doing that, we get then so again, we're putting 2m plus 1 in place of all the k's. And actually r is 0 too, so we should put 0 in place of r here and here. There's going to be 2m plus 1 here, then plus 2, so it'll be 2m plus 3 in the first position, because r is 0. And then in the second position here will be 2m plus 1 plus 4, so it'll be 2m plus 5. Okay, and now m is greater than or equal to 0. So let's start with m is 0. So choosing m to be 0, we get then. So choosing n to be 0 over here, so putting 0 here, I'll have just a3 on this side. Putting 0 here in place of m, we'll just have 2a1 on top. Putting 0 here, I'll have 3. Putting 0 here, I'll have 5. But now from up here, a1 is 0. So therefore, this is going to end up being 0 here. Okay, so our a3 then is 0 because a1 is 0. Now let's choose m to be 1 next. So choosing m to be 1, we have then, so if m is 1 then, so putting 1 in place of m over here, it'll be 2 times 1 plus 3, so a5 equals then putting 1 in place of m here. 2 times 1 plus 1 will be 2 times a3, putting 1 here, 5, putting 1 here, 7. But a3 now, we just showed was 0, so that's going to make a5 0. So a5 is 0. Let's do, say, m equals 2 next. So if m is 2, we have. So if m is 2 now, putting 2 up here, be 2 times 2 plus 3, so it'll be a7 on this side. Putting 2 here, it'll be 3, 4 or 5. So it'll be 2a5. Putting 2 here, it'll be 7. Putting 2 here, it'll be 9. But now a5 is 0. So therefore, it's going to make a7 0. So a7 0. So you should convince yourself then they're all going to be zeros for all these guys here. So we can say in general, so hence then we can say in general then that the a to the 2m plus 3 is going to be 0 for all m. So all the case 1 guys when k is odd will end up being zeros. Okay, so that's case 1 taken care of. Let's do case 2 next. So let me erase case 1 and we'll do case 2 next. Okay, so for case 2, our k will be 2m, so an even number. So I'm going to put 2m in place of all the k's, and again r is 0. So plugging into that, we get then. So we'll have then, putting 2m in place of k here, we'll have a to the 2m plus 2. Then it'll be 2 times ak is 2m. Putting 2m here will be 2m, 0 for r, so it'll be 2m plus 2, and 2m plus 4 here. I can then factor 2 out of these two and 2 out of these two. So factoring a 4 out of both of them, we get then. So factoring a 2 out of this one and a 2 out of this one, we have a 4 in front then. So 2 out of this one will be m plus 1 here. 2 out of this one will be m plus 2 here. Then the 2 and the 4 will go twice here. So simplifying that, we get then. So we get this then. Now let's start choosing m to be different values. Let's choose m equals 0 first. So letting m equal 0, we get then. So letting m equal 0 then in our formula here will be, putting 0 here will be a2 then equals, putting 0 here will be 2a0, putting 0 here will be, or in this one, sorry, 2 times 1 times 2. But now our a0 is 1, so putting 1 there, it looks like we get 1 over 2 squared. Okay, so putting 1 in place of our a0 will be 1 over 2 squared. Alright, let's do now, next let's do m is 1. Okay, so putting 1 in place of m, up here it'll be a4 equals, putting 1 here, a2 over 2 times, putting 1 here, 2, 3, so it'll be this. Now, 2 times 3 is 6, which is also equal to 3 factorial. I'm going to write it as 3 factorial because we want to see a pattern happening here. And 2 you can also write as 2 factorial. So let's do that next. Okay, so pull the a2 out here and wrote the 2 as 2 factorial and wrote the 2 times 3 as 3 factorial. And now a2 is 1 over 2 squared or 1/4. I'm going to keep it as 1 over 2 squared. So making that substitution, then we get. Okay, so making the substitution for a2 as 1 over 2 squared, have it here. Then multiplying this will be then 1 over 2 squared times 2 factorial times 3 factorial. Okay, let's do m equals 2 next. Okay, so letting m equal 2, so it'll be then a6, if you put 2 here, it'll be 4 plus 2 will be 6. Then putting 2 here will be a4, putting 2 there will be 2 times 3 times 4. Let's pull out the a4, so doing that we get then. Okay, so using a4 is this guy up here, so plugging it in here, we get this then. And the 2 factorial times the 3 here, that would make 3 factorial, and the 3 factorial times the 4 would make 4 factorial, and the 2 squared times the 2 would make 2 cubed. So let me write that here. Okay, so it becomes then 1 over 2 cubed, 3 factorial, 4 factorial. And we should be able to start to see a pattern emerge here now. If you look at the a4, it had a 2 squared, 2 factorial, 3 factorial. a6 had a 2 cubed, 3 factorial, 4 factorial. So you might guess then the next one up. So a8 would be the next one. If you're going to guess, you probably guess is going to be 1 over 2 to the 4th, 4 factorial, 5 factorial. Let's just prove that here. So let's do m equals 3 now. So when m is 3, so putting 3 up here, it'll be a8, then it'll be a6, which I pull out in front here. It'll be 2 times 4 times 5. Then we're going to use a6 is equal to this guy here. So making that substitution over here, we get. So substituting this guy for a6 here, which I've done here. Then I can multiply the 2 cubed with the 2. That would make 2 to the 4th. I can multiply the 3 factorial with 4 factorial. Sorry, with 4. That would make 4 factorial. And I can multiply the 4 factorial with the 5. That would make 5 factorial. So let me write it here. So it'd be then 1 over 2 to the 4th, 4 factorial, 5 factorial. So you can see the pattern now. The powers on the 2 are increasing by 1. The factorials are increasing by 1 each of these, each time I go up. So let's try and write the general pattern here. Actually, I'll write the general pattern right here, and I'll explain how I got it. Okay, in general, I'm claiming it's this guy here. So I claim it's, well, it's a to the 2m plus 2, the general guy on this side. I can pull a 2 out like it, so it'll be 2 times m plus 1. Okay, so notice here, this 2 here is related to the 1 here. It looks like it's 1 more. And this 3 is 1 more than that. And this 4 is 1 more than that. So it looks like it's the m value plus 1. That's how I got that. So the 2's to the m plus 1. And one beside it, the factorial guy is the same as that one. See, it's 2, 2, 3, 3, 4, 4. So it'd be m plus 1 factorial. And one after it's 1 more. So that's 2, that's 3, 1 more, 3, 4, 4, 5. So it'd be m plus 2 then factorial. So that'd be the general form. Okay. So let me erase a few things and we'll continue now. Let's summarize what we have. Okay, so summarizing, we have our k equals 2m plus 1, a0 is 1, r is 0, a1 is 0, and a2m plus 1 equals this guy here, where m is greater than or equal to minus 1. I'm using minus 1 here because if I put minus 1 up here, I get a0, which is 1. And also, if you go back to the very beginning in part 1, this is what we assume the series looked like. So we found all the things now. We have the r is 0, and we have this in place of k. So making those substitutions, then we get then. Okay, so putting 0 in place of r and putting this in place of k. I've done that here. Then using the formula that we derived for a2 subscript m plus 1, this guy. So making that substitution here. So this should be our series solution. It's not a power series. Series solution. It's not a power series because if you're stuck in actually maybe power series actually. Looks like we're not going to have any negative exponents on the x here. Okay, so this series should be a series solution for our original differential equation that we're trying to solve. So this guy should be a solution of this differential equation. Okay. If you go back to part 1 of the video, we had some freedom over a0, the r, and a1. I could have chosen different assignments here, but I'd let you check that no matter what assignment you choose, you're going to end up with an equivalent answer here. So I believe there's only one series solution that you'll get using the Frobenius method. You can double check that. So anyway, this is one series anyway solution of this differential equation. Okay, so that concludes the question. So we've found our series solution using the Frobenius method. So we're done. So let's leave it there.